centuries, there have been these math problems that were basically considered unsolvable, like a locked box with no key. Well, today, we're going to take a look at one of those impossible problems, a massive 13th degree polynomial, and watch how a brand new theorem just cracks it wide open.
And here it is. Just look at this thing. What a monster, right? 13 different terms, with powers climbing all the way up to x to the 13th. I mean, just looking at it, you can kind of feel why finding its exact roots, the specific values of x that make this whole thing equal 0, was seen as this just monumental, almost impossible task.
So that's really the big question, isn't it? When all the tools in your toolbox just can't get the job done, what are you supposed to do? For a long, long time, the answer for equations this complicated was, well, you just don't. You get close, you can get an approximation, but a perfect answer? Nope. That, however, is all about to change.
Okay, so to really get why this is such a huge breakthrough, we've got to first understand the old roadblocks. Let's dig into why the classical methods just hit a wall. This really gets to the heart of the whole thing. On one hand, you've got what's called numerical approximation. The best way to think about it is like a blurry photo. You get the general idea, right? You can kind of see the shape, but all the details are fuzzy. It's an estimate. But then on the other hand, you have the exact symbolic solution. That's the crystal clear, high definition picture. It's the perfect, precise answer written out as a beautiful formula. For hundreds of years, mathematicians had to settle for that blurry photo.
And this is the historical giant we're up against. See, back in the 19th century, a brilliant mathematician named Niels Henrik Abel proved something huge. He showed that there's just no universal formula for solving polynomials of degree 5 or higher if you're only using basic stuff like addition, subtraction, and roots, what mathematicians call radicals. Think square roots, cube roots, that kind of thing. So for centuries, his theorem basically put up a giant stop sign. It said that for a ton of problems just like ours, a perfect, exact answer was literally impossible to find.
But what if you didn't have to break down that wall? What if you could just find a way around it? That's exactly where this revolutionary new idea comes into play.
And this right here, this is our key. It's called Ezouidi's Theorem, and it was developed by Professor Mourad Sultan Ezouidi. Now, what's so cool about it is that it doesn't try to break the rules of Abel's theorem. Instead, it just creates a whole new game. It uses this really structured, step-by-step process to find those perfect, crystal clear symbolic roots, even for the polynomials that everyone thought were unsolvable.
And this is the engine that makes it all work. Now don't get bogged down trying to memorize this formula, okay? That's not the point. The main thing to get is that this is like the secret code. It's the algorithm that systematically takes all the numbers from our original messy equation, coefficients, and just starts processing them. It's designed to take all that insane complexity and, one step at a time, boil it down into something way, way simpler. All right, so theory is one thing, but let's see this in action. It's time to put the theorem to the test and actually watch it solve our 13th degree puzzle. The strategy here is just brilliantly systematic. It's a clear, three-step process. First, you just grab all the coefficients, the numbers in front of each x in our big polynomial. Second, you plug those numbers into that special formula to calculate a whole new set of values. We're going to call them s values. And third, this is where the magic really happens. We use those brand new s values to rebuild the entire polynomial into something so much simpler. Okay, so the process begins. We calculate the very first scale value, s0, and we get 0. Huh, okay. Then we calculate s1, and it's also 0. Then s2, s3, s4, all of them 0. A pattern is definitely emerging here, and it almost feels like nothing is happening, right? But what's actually going on is that we're uncovering this deep, hidden structure inside the polynomial. And then, bam, the pattern shatters. When we calculate the next value, s5, we don't get 0. We get a huge number, 13 to the power of 6. This is it. This is the first critical piece of the puzzle. It's the first non-zero key that's going to help us build our new, simplified equation. So when all is said and done, here's the summary of what we found. After running through all 13 SU value calculations, it turns out almost all of them are 0. Only 2 have a value, that S5 we found, and another one, S11. I mean, think about that. That's incredible. These two numbers have basically distilled all the important essential information from that massive 13-term equation. So We've basically transformed the problem from this impossible beast into something manageable. Now it's time for the payoff. Let's use this simplified info to find the exact answers we've been hunting for all this time.
Just look at that. Our terrifying 13-term monster polynomial has been boiled down to this elegant, simple, 3-term equation. All we did was build a new polynomial using our non-zero s values. And this is an equation we can actually work with. We can solve this.
Now, there's one other helpful piece of information we happen to know about this specific polynomial. We know that x equals 1 is one of the roots. And it's a special kind of root, too. It actually shows up 5 times. Mathematicians have a cool name for this. They call it a multiplicity of 5. So, just like that, boom, we've already found 5 of our 13 roots.
And when we solve that simplified equation, we get this. This is the holy grail, the exact symbolic formula for all the other roots. Yeah, it looks complex, I know. The key thing is, it is precise. This is that crystal clear, high definition photo we were talking about, not some blurry guess. This right here is the solution that for centuries the old method said was impossible to find.
So we did it. We cracked the code on a 13th degree polynomial. But let's zoom out. What's the bigger picture here? Why does it even matter to go from a good enough answer to a perfect one?
Well, the implications are actually huge. Think about physics. Exact solutions mean more precise models of how the universe works. Or engineering. It could mean designing stronger and more reliable bridges or buildings. In computer science and cryptography, accuracy isn't just nice to have, it's everything. It's the key to creating faster and more secure algorithms. At the end of the day, exactness is the bedrock of all precision.
And you know, as Professor Ezouidi himself says, this isn't just about solving one tricky math problem. It's about creating a powerful new tool. A tool that pushes the boundaries of what's possible, unlocking perfect answers for a whole class of problems that used to be completely out of reach.
And that leaves us with a really fascinating thought, doesn't it? For centuries, we looked at problems like this one and just saw an impossible wall. But today, we've seen that wall crumble. It really makes you wonder, what other impossible problems out there?